Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, Mr. T here with a math tutorial. This is a second part in a series dealing with trig identities. In part one, we talked about simplifying trig expressions using trig identities. And today we're going to talk about verifying or proving trig identities. It's going to be very similar skills. When we were simplifying, though, we were just working with an expression and we didn't have a specific end goal in mind. When we are verifying or proving trig identities, we are trying to systematically revise one or both sides of the equation to prove that they're equal. And some of the skills we'll be using when we do that will be substitutions using our fundamental or basic identities. We may be factoring, we may be combining fractions or like terms, etc. There's no set specific rule or process that will always work. I'll be giving you some guidelines later in the tutorial. But it's something that you must work on and practice and develop experience with as you work more and more problems. I'll get you started in this tutorial with some ideas about how to approach it with several examples. Let's start with this first example. So this is stated as being a trig identity, and we're trying to prove or verify that indeed these two expressions are equivalent. Now, I'm going to work this problem two different ways to show that there's not always a particular or singular way of working these. One skill we can use is when we have a fraction where we have a single term on the denominator and things being added and subtracted in the numerator is to divide out. So we can divide out here, so we're going to take secant squared and divide it by secant squared, and we also have to divide the 1 by the secant squared. Here we can cancel out the secant squared, so something divided by itself is 1. And here we're going to use the reciprocal identity, so the secant 1 over the secant squared is the cosine squared. And now we're going to use one of the Pythagorean identity substitutions. So remember, we have these Pythagorean identity substitutions. If we subtracted cosine squared here on both sides of the equation, I get another version of the Pythagorean identity, which is 1 minus cosine squared of u here. And that's what we have on our last problem here. We have 1 minus. So using the Pythagorean substitution, we get sine squared of x here, which is what we were looking for. So that checks out. So again, in terms of our steps, we did a divide out. We use the identity principle of something divided by itself as 1. To get this part, we used a substitution using the reciprocal identity. And remember, on the reciprocals, these are all singular terms, but if we square both sides, we would have 1 squared, but 1 squared is 1. We can have those reciprocals both as squares or as single terms. Oops, wrong way. And lastly, we did the, going from this step to this step, we did a Pythagorean identity substitution. And again, we had to modify the Pythagorean identity to get that. So this is one way to work this. I'm just going to work the same problem a second way to show that there's more than one way to attack these. So again, likewise here, if we subtracted 1 from both sides of the equation, we can modify this Pythagorean identity to come up with a new Pythagorean identity. So secant squared minus 1 equals the tangent squared. So we have here secant squared of x minus 1, so that gives us the tangent squared of x over secant squared of x. So we did a Pythagorean substitution. Now I'm going to use the quotient and the reciprocal identities to convert everything to sines and cosines. So the tangent is sine over cosine, and if we square that, we get both of those squares. So this is the quotient ID, and that's all over the secant squared, which is 1 over cosine squared, using a reciprocal identity. Now I have a complex fraction, so we're going to change division into multiplying by the reciprocal. And now I'm going to cancel. Since this is multiplication, we can cancel, and we're left with sine squared of x. Again, verifying what we have. So this identity checks out. So let's summarize some of the skills we use. Notice when I worked that problem, I worked on only one side of the equation, and we started with the side that was the most complicated. So sometimes we may have to work both sides, but in general we're going to attack one side, and we'll start with the more complicated side because that gives us more options of things we can try. We'll be looking for ability to factor combine like terms FOIL as we did in this last problem. We will be doing trig substitutions, and sometimes, as we did with simplifying, if all other things fail, just convert everything to sines and cosines and see if you can proceed. And if you head down a path that doesn't work, you may need to go back to the beginning of the problem, but hopefully you learn something about at least what does not work in working the problem the first time, so you need to try a different starting path. So let's work a couple more examples. Now here we have tangent squared of x plus 1. That is one of the Pythagorean identities, so this is secant squared of x. And here, if we look at the Pythagorean identity and get the sine squared by itself, I've got here 1 minus cosine squared of x. So if I want to flip the order of these, I can multiply both sides of the equation by minus. So if I multiply this by minus, I get negative sine squared of x. Over here I would have minus 1 and plus cosine squared of x. And we can use the addition being commutative to reorder those. So cosine squared of minus 1 is equal to the negative sine squared of x. Now we can convert this to using, so we did a Pythagorean substitution here, and we also had to flip the order of these terms by multiplying by a negative. We could have also factored out a negative 1 of this, and if you factor out a negative 1 and put the minus up here, we would be flipping the order of those. Now I'm going to use the reciprocal identity to put everything in terms of sines and cosines. So this would be 1 over cosine squared of x times negative sine squared of x over 1. So if we multiply our fractions, we've got negative sine squared of x over cosine squared of x. And using our quotient identity, that's the definition of tangent. So we have negative tangent squared of x. So that checks out with what we were looking for here, meaning those match. They're both the same. Let's look at another example. Now this is a little bit more complicated. On this, when we have two fractions added, we want to get a common denominator. And one way to get a common denominator is to take this denominator and multiply it by this fraction. And we have to multiply it. We're not cross-multiplying here. We're going to multiply this fraction by 1 plus sine of x over 1 plus sine of x. And we're going to do the same thing with this denominator. We're going to multiply this fraction by that denominator over itself. So on the top, we end up here with 1 times 1 plus sine of x, so 1 plus sine of x. And here we have plus. And now we have 1 minus sine of x. In our denominator now we have 1 plus sine of x times 1 minus the sine of x. On the top we have two 1's that will combine together. And we have plus sine of x and minus sine of x. They're going to cancel out. And on the bottom we can FOIL this out. Now this is the factored pattern of a difference of two squares. So if you factor that out, you get 1 minus sine squared of x. If that doesn't come automatic for you, then FOIL this out, meaning multiply 1 times both of those things and sine of x times both of those things and combine your like terms. Now here, again, like we did on some of the earlier problems, if I go off to the side here with a Pythagorean identity, equals 1. If I subtract the sine squared over, we see that we have a new version of the Pythagorean identity, which is 1 minus the cosine squared of x. So here we have now 2 over the cosine squared of x. And if we bring the cosine squared up to the top, we're taking a reciprocal, so we end up with 2 times the secant squared of x, which checks out with our original problem there. So again, we got a common denominator. And we did a FOIL. We did a Pythagorean substitution. And remember, we had to kind of tweak or adjust our Pythagorean identity to turn that into a new identity. And then we used a reciprocal substitution, a reciprocal ID. And let's look at, I think here, one last one. Okay. Now here, since there's nothing squared, we can't use any of the Pythagorean identities. So let's just convert everything to sines and cosines. Now we could start on either side. I'm going to start on this side, and let's see how that works out. So we've got now tangent using the quotient identity is sine of x over cosine of x. And cotangent is the, whoops, wrong mistake there, cosine of x over the sine of x. And like we did in the last problem, we want to get a common denominator. So I'm going to multiply this by the other denominator, sine of x over sine of x, and multiply this by cosine of x over cosine of x. So we use this denominator over here, this denominator there. So now on the top we have sine squared of x plus cosine squared of x over sine of x cosine of x. This, using a Pythagorean substitution, becomes 1. And now if we look at where we want to head, we've got two trig functions here. So I've got a couple choices. I could split this into 1 over sine of x times 1 over cosine of x. So essentially, we're unmultiplying those. And using the reciprocal identity, this is the cosecant of x, and this is the secant of x. And we've now just proved this because we can use the commutative property of multiplication to change the order of those. So now we've proven it that way. If we got to, say, this point here, and you weren't sure how to get this, we could go over now and work the other side. So we could turn this into 1 over cosine of x times 1 over sine of x, and then multiply those together. And again, use the commutative property of multiply and show that those two things are the same. So we could have again split this up and kept working on just one side of the problem, or we could have gotten to a point and maybe got stuck, didn't know what to do, so we could then go and start working the other side of the problem. Ultimately, you want to get to the point where you've got the same expression on both sides. When we've done that, we've proven. And again, we did common denominator. We did the Pythagorean substitution. We did, here we did the, essentially split the fraction, or factored it, and then we used a reciprocal ID. And we used the commutative property. So good luck with proving these, and stick with it. It takes practice and experience, so don't give up, don't get frustrated, and do your best.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?